A black hole does not need claws, fire, or a crushing surface to become terrifying. Its danger is quieter than that. Cross the horizon of a giant one, and nothing may happen at first. A clock may still tick, a heartbeat may continue. The darkness may feel almost calm, but from that moment on, the outside universe is no longer part of the future. Every road, even the road taken by light, bends inward. Could life survive there for a few seconds, a few minutes, or in some stranger form beyond ordinary biology? Welcome to calm space science. If this journey into the deepest edge of physics feels worth taking, a like, a subscription, and a share would help this quiet corner of science reach more curious minds. Thank you for spending your time here. What time is it where this video finds you, and where are you watching from? Leave it in the comments. Now, the fall begins. At the edge of a black hole, the universe does not announce that an ending has begun. There is no surface waiting in space, no wall of matter, no glowing shell that marks the last safe border. There is only a boundary drawn by gravity itself, a place where every possible path that still belongs to the future turns inward. Outside it, light can still climb away if it has enough direction and energy. Inside it, even light has no route back to the wider cosmos. This boundary is the event horizon, and it is the first threshold in the question of survival. It is not the place where all things are crushed. It is the place where escape stops being part of the geometry. For an observer far away, anything falling toward this border appears to slow, dim, and redden, as if the black hole is stretching the last moments of the fall across an almost endless outward time. For the falling object itself, the story is different. Its own clock keeps moving. Its own path continues. The horizon is crossed not as a dramatic surface, but as a change in what the future allows. Survival inside a black hole begins with this mismatch between appearances from far away. The fall seems frozen near the edge, while along the falling path, the edge may pass quietly beneath notice. A black hole forms when mass curves space-time so severely that no outward direction remains beyond a certain radius. This radius depends on mass. A black hole with the mass of a star has an event horizon only a few kilometers wide, while a supermassive black hole, like the one at the center of the Milky Way, has a horizon spanning millions of kilometers. This difference matters deeply, because gravity itself is not the only danger. The real danger near the horizon is the unevenness of gravity from one part of an object to another. A small black hole concentrates its curvature into a much tighter region, near its edge. The pull on the near side of a falling body can be far stronger than the pull on the far side. This difference creates tidal force, the same basic effect that raises oceans under the moon, but taken to an extreme beyond ordinary comparison. In such a place, survival is not limited by the horizon. It ends before the horizon is reached, because matter is stretched along the direction of the fall and compressed sideways until structure can no longer remain structure. An organism, a spacecraft, a rock, or an atom all face the same larger truth geometry becomes stronger than form. But for a much larger black hole, the horizon is spread across a far wider region. The curvature at the edge can be gentle enough that a falling object might cross without feeling anything sudden at all. This is one of the first surprises in black hole physics. The larger the black hole, the less violent its horizon can be. The boundary is absolute in meaning, but it is not always intense in local experience. A traveller falling into a supermassive black hole could pass the event horizon, while instruments continue to function, clocks continue to tick, and nearby objects continue to drift alongside. The horizon is fatal because of direction, not because it must be locally destructive. Once crossed, every ordinary future points deeper in. A rocket inside the horizon cannot fly outward in the sense that a rocket outside can. It may fire its engines, change its path, and slow or speed its fall relative to nearby matter, but the deeper future still lies inward. The event horizon is less like a gate, and more like the point in a river where all currents now lead over a hidden drop. Even if the water near the crossing is smooth, this gives the question of survival a divided answer almost from the beginning. Could something survive crossing the horizon of a black hole under the right conditions? Known physics allows the answer to be yes. Could something survive indefinitely inside after crossing? Known physics gives a darker answer. The interior is not a stable chamber. It is not an empty cave behind a cosmic door. It is a region where the structure of space-time itself changes the meaning of waiting, moving, and remaining. In a non-rotating black hole, the singularity is not simply a dense point sitting at the center like a target. In the deep geometry of the interior, the singularity lies in the future of everything that crosses the horizon. Avoiding it is not like avoiding a place. It is like avoiding tomorrow. This does not mean the traveller feels that truth immediately. In a large enough black hole, there may be a span of proper time after the crossing, a private interval along the falling path. During that interval, instruments might record the darkness, the changing directions of light, and the quiet certainty that no message can return. The survival is real, but temporary, inside a future that has narrowed. Black holes also differ by spin, mass, and environment. Though real astrophysical black holes are expected to be defined mainly by mass and rotation. Spin matters because most stars and gas clouds rotate, and their collapsed remnants keep that motion in altered form. A rotating black hole drags space-time around with it, twisting the surrounding geometry. This does not make escape from inside the horizon possible in ordinary relativity, but it does complicate the interior. The threshold may no longer be the only horizon. The path inward may involve regions where time, direction, and stability behave in ways that are difficult to interpret. These rotating interiors appear in mathematical solutions, yet mathematics is not the same as a safe destination. Real black holes absorb radiation, gas, stars, magnetic fields, and the faint remnants of the universe around them. Every disturbance may change what the interior becomes. The clean diagrams of theory give a necessary guide, but they may not describe the final conditions that matter must face. This is why survival cannot be answered by a single image of a black sphere. A black hole is not one environment. Near a small one, the horizon itself can be surrounded by lethal tidal distortion. Near a quiet, supermassive one, the crossing can be gentle, but the deeper interior remains unavoidable. Near an active black hole with a hot accretion disk, the space outside the horizon may be filled with radiation, fierce enough to make survival impossible long before the boundary arrives. In such a system, the danger is not only gravity, it is heat, particle storms, magnetic turbulence, and radiation from material that has not yet disappeared. The calmest possible crossing would require a large black hole, a quiet surrounding environment, and a path that avoids violent matter on the way in. Even then, survival means only that the traveller remains intact beyond the first threshold. It does not promise a home. It does not promise a return. It does not promise that the laws known outside will remain enough to describe the end of the fall. The event horizon becomes a strange dividing line between two kinds of ignorance. Outside, science can observe the black hole by its effects, the orbits of stars, the glow of accreting gas, the bending of light, the waves released when black holes merge. Inside, the evidence is sealed away. No experiment beyond the horizon can report back to the universe that launched it. General relativity can trace possible paths inward, and it can show where ordinary descriptions fail. Quantum theory can describe matter and fields in other extreme settings, but it does not yet give a complete account of gravity at the deepest point. Between these pillars lies the missing theory that would decide what happens when curvature, energy, and information reach their most severe limit. Until that theory is known, the interior remains both a prediction and a question. Still, the first threshold gives a careful answer. A black hole does not instantly destroy everything at its horizon. Under certain conditions, crossing can be survivable for a while. The size of the black hole, the strength of tidal forces, the presence of radiation, and the path of descent all decide how much of a future remains. But once the event horizon is crossed, survival changes meaning. It is no longer the ordinary survival of a creature in a place able to turn around, signal home, or choose another direction. It is survival along a narrowing road inside a geometry that points every road inward. The black hole does not need to strike at the threshold. It only needs to remove all exits. Beyond that edge, the universe still exists, but it is no longer part of the falling future. The first answer is severe. Something may survive inside a black hole briefly, but the horizon turns survival from an open condition into a countdown written into space-time itself. Gravity begins gently when it is spread across enough distance. This is the quiet fact that makes a black hole stranger than its reputation. The common image is a cosmic drain, a crushing object with a terrible surface, something that strikes anything approaching it with instant force. Yet a black hole is not a hard sphere. It is not made of dark material with a crust or shell. It is a region of space-time where gravity has arranged every possible outward path into failure. The event horizon marks that change, but the horizon itself is not substance. Nothing is sitting there to be touched. Nothing has to burn, scrape, or collide at the crossing. A falling body can pass through a horizon without meeting any local sign that the boundary has been crossed, provided the black hole is large enough and quiet enough. This does not make the horizon safe. It makes it more unsettling. The danger is absolute, but it can arrive without drama. The deepest trap in the universe may begin with no jolt, no flash, and no surface underfoot. A black hole is less like an object in space than a failure of space to provide a way out. Around ordinary planets and stars, gravity bends paths but leaves escape possible. Light leaving the sun loses a little energy as it climbs, but it still departs. Near a black hole, the curvature grows so severe that there is a boundary where escape speed would have to exceed the speed of light. Since light is the fastest signal the universe permits, the boundary becomes final. But this description can be misleading if it makes the horizon sound like a place where gravity suddenly becomes infinite. It does not. At the horizon of a large black hole, a falling observer can be weightless because everything nearby is falling together. The local experience can resemble floating in deep space. The black hole is revealed not by pressure against the body, but by the global shape of the future. A small laboratory might continue to behave normally for a short time. A clock ticks. Light crosses the cabin. The difference is that no outward beam can ever reach the distant universe again. The room may feel ordinary while its destiny has become extraordinary. The scale of the black hole decides how gentle this deception can be. The size of the event horizon grows in direct proportion to mass. When mass doubles, the horizon radius doubles as well. Volume, however, grows much faster, because a sphere with a larger radius contains far more room. This leads to one of the most counterintuitive facts about black holes. The average density associated with a black hole can become lower as the black hole becomes larger. A stellar mass black hole forms from a collapsed star and packs several suns into a region only a few kilometers across. Its average density is enormous. A supermassive black hole can contain millions or billions of solar masses, yet its horizon is so wide that the mass is spread across a vast volume if averaged in the simplest way. The interior is not a normal container, but the comparison still reveals why the horizon can be calmer for larger black holes. Curvature at the edge is weaker when the edge lies far from the deepest central region. A small black hole bends spacetime sharply near its horizon. A large one bends spacetime across a wider domain. This is why an object can be destroyed outside the horizon of a small black hole, but remain intact while crossing the horizon of a giant one. The key is not the total pull alone. It is the difference in pull across the body. If the feet of a falling astronaut are much closer to the black hole than the head, the feet follow a more strongly curved path. The body is stretched. If the difference is small, the body feels little immediate stress. Near a supermassive black hole, the horizon can be so broad that the gradient across a human scale is modest. For a brief interval, survival is not forbidden by the horizon itself. The falling body is lost to the outside universe, but it is not necessarily torn apart at the boundary. This strange calm also depends on the black hole being isolated. Many real black holes are surrounded by accretion disks, clouds of gas and plasma heated by friction, compression, magnetic fields, and orbital speed. Matter falling in can spiral, heat, radiate, and launch jets before it ever crosses the horizon. In that environment, survival may end outside the horizon because the surroundings are hostile. Radiation can damage molecules, high-energy particles can pass through shielding, and heat can overwhelm structure. A quiet black hole offers the cleanest version of the question. In that cleaner case, crossing the horizon becomes almost invisible locally, while still being completely irreversible. The absence of a surface also changes how the word inside should be understood. Inside a planet means beneath its surface, surrounded by material. Inside a star means within plasma, pressure, light, and nuclear reactions. Inside a black hole means being beyond a causal boundary, in a region where signals cannot escape to infinity. It is a relationship to the rest of the universe, not simply a location within an object. Once past the horizon, the falling traveller does not enter a chamber of darkness with walls around it. The traveller enters a geometry where every future directed path leads deeper. This is why ordinary ideas of hovering fail. Outside the horizon, a rocket can fire its engines and maintain a fixed distance from the black hole if the engine is powerful enough. At the horizon, maintaining a fixed position would require an impossible acceleration. Inside, staying at a constant radius is not a physical option, because the radial direction behaves more like time. Moving towards smaller radius becomes as unavoidable as moving from the present into the future. The black hole is not pulling from a surface below. It is rewriting the set of possible futures. Light itself shows this change. Outside the horizon, a lamp can send beams in many directions. Some beams fall inward, some curve around, and some escape. Closer to the horizon, the escaping cone narrows. At the horizon, even an outward beam remains on the boundary. Inside, all future-like cones tilt inward. Every beam, no matter how it is aimed locally, moves toward the singular fate. This tilting is not something a falling observer sees as a mechanical wall. It is the mathematical expression of lost escape. Space and time remain locally normal in a small enough free-falling region, but the global arrangement has changed. The light from a flashlight still races away from the bulb at light speed in the local frame. Yet the future of that light is no longer outside. Its path belongs to the black hole. This calm crossing is sometimes mistaken for hope. It is more precise to call it a delay. The horizon may not kill immediately, but it removes every long-term strategy known to ordinary physics. There is no orbit inside the horizon of a non-rotating black hole that remains safely suspended. There is no path that loops back into the external universe, even in rotating black holes, where the interior structure becomes richer and more uncertain. The event horizon still marks the end of return. Survival, therefore, has to be measured in proper time, the time carried by the falling object itself. For a stellar mass black hole, that time from horizon to final destruction can be extremely short. For a supermassive black hole, it can be longer. This creates a haunting kind of survival. The traveller may continue to exist, but all messages become private to the interior. Scientific knowledge can be gathered, yet it cannot report back. Experience can occur, yet it is sealed away by geometry. The calmness of a large horizon sharpens the mystery because it separates the first crossing from the final end. It shows that black holes are not simple machines that instantly grind anything they meet. They can allow matter to pass into a region that is locally uneventful and globally doomed. They can make the boundary and the fall feel like nothing at all. They can let an organism, a probe, or a fragment of rock remain itself for a little while after the outside universe has become unreachable. But this quiet does not weaken the trap. It only reveals the trap in its purest form. A surface can be struck, avoided, drilled, or climbed. A horizon is different. It is a promise made by space-time that every allowed future has changed direction. The absence of a surface leaves no place for resistance to begin. The black hole does not have to crush at the edge, because the edge has done something deeper. It has removed the outside from the list of possible tomorrows. A black hole may have no surface, but it still has a shape in the way gravity changes from one place to the next. That change is the force that decides whether anything can remain whole. Gravity near any massive body is never perfectly equal across an extended object. The side facing the source falls a little more strongly than the side farther away. Around Earth, this difference lifts the oceans into tides, gently stretching the planet and its seas. Near a black hole, the same principle grows into one of the most severe limits in nature. It is not simply gravity that destroys. It is uneven gravity, gravity with a gradient, gravity that pulls one end of a body into a different future from the other end. This is why the question of survival cannot stop at the event horizon. Before the horizon is crossed, the falling object must pass through a region where space-time may begin to stretch, shear, and compress matter until shape itself becomes temporary. The familiar name for this fate is spaghettification, a word that sounds almost playful for a process that is really a quiet failure of structure. A body falling feet first toward a compact black hole is drawn out along the direction of descent. At the same time, it is squeezed from the sides, bones, metal beams, molecules, and eventually atoms are asked to follow paths that no longer remain parallel. Each nearby piece of matter tries to fall freely, and because the curvature is different across even a small distance, free fall becomes separation. There is no single pull that can be resisted by an engine or a wall. The problem is that different parts of the same object are being assigned different accelerations. A spacecraft could strengthen its hull, but the hull itself has a limit. A living organism could float weightlessly for a moment, but its tissues are extended objects, built from cells, fluids, proteins, and electrical gradients. They depend on the assumption that nearby parts of the body remain nearby. Tidal force erases that assumption. The smaller the black hole, the sharper this erasure becomes. In a stellar remnant only a few times the mass of the Sun, the event horizon is close to the central region where curvature is extreme. At that horizon, the difference in gravity between the near and far sides of a human-sized body could already be fatal, long before any careful observation of the interior becomes possible. The body may be pulled into a narrowing thread of matter. A spacecraft fares no better if the gradient exceeds the strength of its materials. It may break first as a machine, then as fragments, then as plasma and radiation, each layer of structure giving way to a deeper layer of physics. From the outside, the process may be hidden by time dilation and fading light. From the falling frame, it is not hidden. It is the increasing fact that different parts of the same object can no longer share the same fall. A supermassive black hole changes the order of events. Its horizon is enormous compared with the scale of a person or ship, and the curvature at that boundary can be mild. In such a case, the tidal forces at the event horizon may be too small to notice. An object crosses intact, and only later, deeper inside, does the gradient rise. This is the crucial difference between surviving a horizon and surviving a black hole. The first may be possible in a giant black hole. The second grows more doubtful with every inward moment. As the falling path continues, the distance to the central fate shrinks, and the variation in curvature becomes stronger. The same effect that was gentle at the horizon becomes decisive farther in. The black hole does not need a surface because the geometry tightens on its own. Tidal stress rises without needing contact. The body is not struck by something. It is separated by the shape of space-time. This makes scale the hidden judge of survival. A small creature, a bacterium, a grain of dust, or a single molecule experiences less tidal difference across its own size than a large spacecraft does. Smaller things can survive stronger gradients for longer because their near and far sides are closer together. In that limited sense, survival favors smallness. A tiny object may remain structurally intact after a larger one has already been pulled apart. But this advantage has boundaries. Any living system, no matter how small, requires organization. It needs chemical bonds, energy flow, internal gradients, and some separation between inside and outside. Tidal forces eventually act across molecular and atomic scales as well. Before that point, other dangers may arrive: radiation, collisions with infalling matter, extreme blue-shifted light, and the growing instability of the interior environment. The smaller scale delays the problem. It does not remove it. For ordinary life, the difficulty is sharper because biology is not merely matter staying together. A living cell is a pattern maintained away from equilibrium. It must preserve membranes, proteins, genetic information, liquid chemistry, and controlled exchange with its surroundings. Near a black hole, a cell does not only ask whether its atoms can remain attached, it asks whether its processes can continue at all. Tidal distortion can stretch membranes, disrupt fluid flow, and pull organelles along different paths. Radiation can damage complex molecules. A bacterium frozen in a protective shell might remain intact through gentler phases of the fall, especially into a large and quiet black hole. But intact is not the same as alive in any active sense. Dormant survival, chemical preservation, and conscious survival are different claims. For a complex organism, survival requires the brain, circulation, and internal chemistry to remain coordinated. A supermassive horizon may allow that briefly. Rising tides deeper in do not. Planets and stars face the same rule on larger scales. If a star passes too close to a massive black hole, but does not fall directly in, tidal forces can tear it apart in a tidal disruption event. The star becomes a stream of gas, some flung outward, some wrapped into a luminous disk. The black hole does not touch the star. It unravels it by making one side fall differently from the other. A planet can be stripped in the same way if it passes close enough. Oceans, atmospheres, crusts, and cores would not share a single path for long. These events show that black hole danger is not confined to the invisible interior. The region outside can already be a place where gravity acts like a cosmic sorter, separating matter according to distance, density, and strength. For survival, the safest path is not only one that crosses a large horizon, it is one that avoids strong tidal disruption before reaching it, avoids hot surrounding gas, and enters with as little disturbance as possible. Even then, the safety is temporary. Tides also reveal why falling freely is not the same as being safe. In ordinary orbit or descent, free fall removes the feeling of weight. Astronauts appear weightless not because gravity is gone, but because everything around them follows nearly the same path. Near a black hole, that sameness eventually fails. A falling laboratory can be locally weightless while slowly stretching. At first, the effect may be measurable only by precise instruments, a tiny drift between floating test masses. Then the drift grows. The test masses move apart in one direction and together in another. The laboratory becomes a map of curvature. Later, no material strength can hold the map still. Bolts, welds, crystals, and cells all become attempts to enforce a shared motion where space-time no longer allows one. In this sense, spaghettification is not a force in the ordinary contact sense. It is the failure of an extended object to remain a single local system, as the geometry around it becomes too steep. The final answer given by tides is therefore conditional but severe. Something can survive where tidal gradients are weak enough across its own size. A large black hole can make the event horizon passable. A small object can endure longer than a large one. A quiet environment can prevent radiation and collisions from ending the attempt early. But all these advantages only move the boundary of destruction inward. They do not create a lasting refuge. As the fall continues, the tidal field strengthens, and every form of structure is tested at smaller and smaller scales. The black hole turns survival into a race between size, strength, and remaining time. For a while, geometry may be gentle. For a while, the fall may feel empty. Then the difference between one end and the other begins to matter more than the object itself. Tides decide that survival is not only about crossing the point of no return, it is about how long anything can remain one thing after the universe has begun pulling its parts into different futures. Time becomes strange before the fall is finished, because black holes do not only bend paths through space, they bend the rate at which clocks divide the future. Far from a black hole, a clock ticks in the usual way, carried by the calm geometry of weaker gravity. Closer in, the same kind of clock ticks more slowly when compared with one kept far away. This is gravitational time dilation, and it is not an illusion made by distance or imperfect observation. It is a difference in how space-time assigns duration to different paths. Near a black hole, time is not one universal river flowing everywhere at the same pace. It becomes local, shaped by height in a gravitational field, by motion, and by the curvature surrounding the horizon. The question of survival therefore gains a second clock. There is the clock carried by the falling object, measuring its own remaining experience, and there is the clock of the distant universe, watching the fall through light that loses energy as it climbs away. Between them opens a quiet split. One path continues inward. The other sees the same descent stretch toward stillness. For a distant observer, an object falling toward the event horizon never seems to cross in a visible way. The light it sends outward must fight harder and harder to escape. Each signal climbs from deeper gravity, losing energy on the way, so its wavelength lengthens and its color shifts toward red. Then beyond visible light, The signals also arrive more slowly, spread farther apart by the geometry between the falling object and the observer. A clock on the falling object appears to run slower and slower. Its image grows dimmer. Its final approach seems to freeze near the horizon, not as a bright statue, but as a fading ghost of information thinned across time. This outward view can make the horizon seem like a place where nothing ever enters. Yet the falling object does not share that endless delay. Its own proper time remains finite. It crosses the horizon and continues inward. The contradiction is only apparent because the two descriptions belong to different vantage points connected by light that can no longer keep reporting the same story. The outside universe receives older and older news from the fall, delayed and weakened until it is effectively gone. The inside path simply goes on. The same event can be both unreachable in the outside record and completed along the falling world line. In everyday life, the difference between observers is usually tiny. Around compact objects, the difference becomes large. Around a black hole, it becomes extreme. Time dilation near the horizon means that the falling object sees the outside universe distorted in a different way as well. Light from the wider cosmos can be shifted, bent, and concentrated depending on the path of the fall. If the traveller looks outward before crossing, the rest of the universe does not simply continue as a normal sky. The view can be compressed, brightened in some directions, distorted by gravitational lensing, and altered by motion. After the crossing, the outside universe is still part of the path light reaching the falling observer for a while, but it is no longer reachable by any return signal. The falling object can receive traces of the cosmos, but it cannot send its own trace back. Time becomes a one-way exchange. Information can fall in. It cannot climb out. The phrase that time stops at the horizon is too simple. For the falling object, time does not stop there. A heartbeat would continue if the body remains intact. A chemical reaction would proceed if conditions allow it. A computer clock would count cycles. A probe could collect measurements for as long as its structure and power survive. Locally, the laws of physics do not suddenly pause at the event horizon of a large black hole. The stopping belongs to the distant description, to the way outgoing light is stretched and delayed. The black hole creates a deep disagreement between external time and internal experience. From far away, the fall becomes an ever-dimming approach. From within the fall, the horizon is crossed and the remaining future contracts. This distinction matters because survival is always measured by some clock. An organism does not survive according to the infinite patience of a distant telescope. It survives according to its own internal processes. Those processes may continue briefly beyond the horizon, even while the outside universe never sees a clean crossing. Yet time dilation offers no escape from the final geometry. It changes the relationship between clocks, not the direction of possible futures. In a non-rotating black hole, once the horizon is crossed, the singularity lies ahead in a finite amount of proper time. A larger black hole can grant more of this private time than a smaller one. This interval is not a place of safety, only a longer descent. It may be long enough for instruments to record strange skies, for signals to be sent inward, or for matter to remain organized if tidal forces stay mild. But no amount of slowed external time turns the interior into a permanent refuge. The falling clock does not borrow eternity from the distant universe. It carries its own finite duration toward a future where known classical physics predicts breakdown. The strange gift of time dilation is not immortality. It is separation. The outside may age differently, while the traveller experiences only the time along the path. Near a rapidly spinning black hole, the story becomes more subtle. Rotation drags space-time around. allowing stable orbits closer to the horizon than a non-rotating black hole permits. This is why theoretical discussions sometimes place planets or spacecraft near enormous spinning black holes, where time runs far slower than it does far away. In principle, a world orbiting outside such a horizon could experience severe time dilation without immediately falling in, provided the black hole is very massive, rapidly rotating, and not surrounded by lethal radiation. But this is still outside the horizon. It is an orbit in the external universe, not survival inside the black hole. The distinction is crucial. Time dilation outside can let one region age slowly compared with another. Time dilation inside cannot open a road back. Once the boundary is crossed, the clock may continue, but its future is sealed. The universe beyond may race onward in comparison, but that distant future does not become a reachable destination. There is also a quieter danger in the light that falls with the traveller as the descent continues. Radiation from the external universe can be blue-shifted in certain frames, meaning its energy is increased rather than reduced. Light that was harmless far away can become more energetic when measured by someone moving through the curved geometry. Near inner horizons in rotating black holes, theoretical calculations suggest that in falling radiation and perturbations may pile up into severe instabilities. This is not the familiar spaghettification of a body by tides, but a storm of energy shaped by time itself. The same gravitational delay that makes outward signals fade can make inward accumulated radiation dangerous. For survival, this means that a gentle event horizon is not the whole story. A traveller may cross without being torn apart, only to encounter later regions where the past of the black hole, the matter that entered before, and the radiation that follows behind become part of the hazard. Time inside a black hole is not empty. It carries history inward. The slow trap of time therefore has two faces. From outside, time appears to protect the universe from ever witnessing the final crossing. The horizon becomes a fading limit, a surface approached but never cleanly seen as past. From inside, time offers a brief continuation, a private corridor where the fall proceeds normally enough until the deeper conditions grow extreme. Neither face grants rescue. The first hides the crossing from external observation. The second allows experience to continue beyond the point where escape is gone. Together they show why black holes are not merely places of strong gravity. They are places where the agreement between clocks is broken so deeply that survival must be defined by perspective. A distant astronomer may never receive the last message. A falling probe may keep recording after its last outward signal has already become too faint to matter. The universe outside may stretch into a long future, while the object inside carries only a narrowing present. The question of whether anything can survive inside a black hole becomes a question of whose time is being counted. By the falling clock, survival may continue past the horizon. By the distant clock, the evidence fades before completion. By the geometry of the interior, both stories end with all future paths bending inward. Time does not stop the fall. It only makes the fall belong to two different realities, one that watches forever from outside and one that continues into the dark. Most black holes in the real universe are not still. They are born from rotating stars, fed by orbiting gas, and shaped by the angular momentum of everything that falls toward them. Rotation is difficult for nature to avoid. A cloud collapses and spins faster as it shrinks. A star dies while carrying the memory of its earlier motion. Matter spirals inward rather than dropping straight down. Many black holes are therefore expected to spin, sometimes very rapidly, and spin changes the darkness around them. It does not make the event horizon a door that can be opened again. It does not turn the black hole into a safe tunnel by itself. but it does reshape the geometry. And with that reshaping comes a deeper uncertainty about what falling inside may mean. A non-rotating black hole is already strange enough, with every future path inside the horizon leading toward the singularity. A rotating black hole adds motion to the trap. Space-time itself is dragged around the black hole, as if the surrounding universe has become a slow whirlpool with no material water. This effect is called frame dragging, and it is a real prediction of general relativity. Around a spinning mass, the local meaning of standing still changes, near a rotating black hole. There is a region outside the event horizon where nothing can remain motionless relative to the distant stars. Anything there must be carried around in the direction of the spin, not because it has touched a surface, but because space-time has been set into rotation. This region is called the ergosphere. It lies outside the horizon, so escape from it is still possible under the right conditions. In principle, the rotation of a black hole can be tapped for energy there. For survival, however, the ergosphere is only the outer warning. It may allow extraordinary orbits and energetic interactions, but it remains outside the true boundary of no return. Once the event horizon is crossed, even rotation cannot restore an ordinary outward path. The falling object is still inside a region sealed from the distant universe, yet the inner geometry is no longer the same as the clean, non-rotating case. The mathematical solution for an ideal rotating black hole, known as a Kerr black hole, contains not only an outer event horizon, but also an inner horizon, sometimes called a Cauchy horizon. This inner horizon is one of the most unsettling features in black hole theory. In the ideal equations, it marks a place where the predictable flow of space-time appears to change character. Beyond it, the simple statement that every path ends at the same unavoidable central future becomes harder to preserve. The singularity itself is not a point in the same way as in the simplest black hole. In the ideal rotating solution, it appears as a ring. That ring is surrounded by mathematical possibilities so strange that they have inspired ideas of passages, other regions, or altered futures. But these possibilities live first inside equations, and equations can be fragile when nature adds noise. A real black hole is not an empty, perfect solution. It receives radiation from the universe. It contains matter that fell in earlier. It is disturbed by gravitational waves, magnetic fields, particles, and the faint background glow of space. Near an inner horizon, these disturbances may not remain harmless. Relativity suggests that signals and infalling material can be enormously blue-shifted there, meaning their energy can grow without bound in the local description. This leads to a phenomenon often called mass inflation, where the inner horizon becomes unstable under even tiny disturbances. For anything trying to survive, this may be fatal. The outer horizon of a supermassive rotating black hole might be calm, but the inner horizon could become a place where accumulated history turns into a wall of energy and curvature. The black hole remembers what has fallen into it, and that memory may meet later arrivals in a violent mathematical convergence. This is why the dream of using spin as a route through the black hole remains deeply uncertain. The clean Kerr geometry hints at openings that the messy universe may close. Survival inside a rotating black hole depends on which version of the interior nature actually builds. If the ideal solution were exact, the falling object might encounter a more complicated sequence than the direct fall into a central singularity. The path could pass through regions where the direction of time and space becomes difficult to map with ordinary intuition. But if the inner horizon is unstable, then the traveller meets an extreme concentration of energy before any exotic continuation can matter. Most physicists treat the stable passage suggested by the ideal equations with caution, because real black holes are expected to be perturbed, a single photon falling in, a trace of cosmic microwave background radiation, or the remnants of earlier infall may become important when amplified by the interior geometry. Rotation also changes the outside approach in ways that can help or harm survival before the horizon. Around a spinning black hole, the innermost stable circular orbit can lie closer to the horizon for matter moving with the spin. Gas can spiral deep into the gravitational well before plunging, releasing vast amounts of energy. This is one reason accretion disks around black holes can glow so fiercely. A spinning black hole can be surrounded by some of the most energetic environments in the cosmos. For a traveller or probe, that brilliance is a warning. A black hole quiet enough for a gentle crossing would need little nearby gas, little dust, and a path that avoids the heated disk and jets. Spin by itself is not protective. It may allow more complex motion, but it can also power violence outside the horizon through surrounding plasma and magnetic fields. The safest imagined descent would be into a very massive, isolated black hole, along a path that does not cut through its brightest feeding structures. Only then does the interior question become more than an immediate problem of radiation and impact. Once inside, rotation introduces the possibility that the singularity is not simply waiting as a crushed point in the future. In the ideal model, the ring singularity is tied to the axis and spin of the black hole. Around it, the mathematics suggest regions where the usual order of events might break down. Some speculative interpretations have treated this as a hint of bridges to other universes or distant places in the same universe. But such language must remain careful. A mathematical extension is not the same as a traversable route. It may describe what the equations allow when nothing disturbs them, not what an actual falling body can experience. The smallest amount of realistic energy may alter the interior completely. Quantum effects, absent from the classical Kerr solution, may also become essential where curvature grows large. The rotating black hole therefore deepens the mystery without granting a clear escape. It replaces the simple certainty of a central end with a more complex uncertainty that may still end in destruction. For living matter, the difference may be less hopeful than it first appears. A human organism, a seed, a microbe, or any organized chemistry needs a stable local environment. It needs forces that do not tear it apart, radiation that does not erase its information, and time enough for its processes to continue. The outer horizon of a giant spinning black hole might satisfy the first condition briefly. The deeper interior likely fails the rest. Frame dragging does not protect cell membranes. An inner horizon instability does not respect nervous systems. A ring singularity, if it survives in any meaningful sense, lies in a region where classical language is already strained. The living system carries ordinary chemistry into a place where ordinary chemistry is not the central law. It may cross the horizon alive, but it does not gain a habitat. It enters a moving geometry whose deeper regions are still governed by pressures, shifts, and instabilities that life was never built to endure. Rotation, then, is not a rescue from the black hole. It is a complication of the verdict. It shows that the interior may not be a simple plunge toward a central point. It reveals horizons within horizons, trapped motion within dragged space-time, and mathematical futures that seem to widen before they likely collapse under reality. It keeps the question open enough for speculation, but not open enough for confidence. The black hole can spin, twist, and store energy in its geometry. Yet the first horizon still separates all survivors from the outside universe, and the deeper structure may be even more dangerous than the quiet crossing suggests. Motion reshapes darkness. But it does not make darkness safe. It only makes the path inward less simple, less settled, and more deeply hidden from everything that remains outside. Inside the horizon, the word inside begins to lose its ordinary meaning. In daily life, inside means surrounded by boundaries that can be mapped from the outside. A room has walls, a planet has layers. Even a star has a structure that can be described as deeper or shallower, closer to the center or farther from it. A black hole interior does not behave like that simple picture. The event horizon is crossed as a boundary, but what follows is not a chamber waiting behind a door. It is a region where the geometry of space-time changes so deeply that direction itself must be reinterpreted. Outside the horizon, moving inward or outward is a choice of path through space. Inside, the inward direction takes on the force of time. It is no longer merely where something can go. It is where every future must go. The center is not only a location ahead in space, but a moment ahead in time. The simplest black hole used to explain this is a non-rotating, uncharged black hole. The clean mathematical case known as a Schwarzschild black hole. No real black hole is likely to be perfectly like this, because real objects rotate and live in a universe filled with radiation and matter. Yet the simple case remains powerful because it reveals the basic transformation at the horizon. Outside, the radial direction is spatial. A spacecraft can move to a larger radius or a smaller radius. It can orbit, hover with enough thrust, fall inward, or escape outward if it has sufficient energy. Time points forward, but space still offers alternatives. Inside the horizon, those alternatives are gone. The coordinate that once described distance from the center behaves more like a time coordinate. Smaller radius lies ahead in the same unavoidable sense that tomorrow lies ahead outside. A traveller can still move locally, turn, fire engines, and rearrange position relative to nearby objects. But none of those motions change the deeper direction of the future. To resist the fall is not like climbing a hill. It is like trying to remain in yesterday. This is why the singularity is so often misunderstood. It is usually pictured as a point at the center, an infinitely dense speck hidden in the blackness. That image can be useful from far away, but inside the horizon it becomes misleading. In the non-rotating case, the singularity is not simply a target floating somewhere in front of the falling traveller. It is a future boundary of space-time. Every path that continues forward eventually reaches it, just as every ordinary path through life eventually reaches later time. It is not approached because matter is aimed at a central object. It is approached because the geometry allows no future that does not end there. In this view, the singularity is less like a place and more like an event that all interior histories are forced to share. The falling traveller does not choose to go toward it. The traveller exists in a region where going forward means going toward it. This change can be described through light cones, the invisible maps of what signals can do from any event. In ordinary space far from a black hole, a flash of light spreads outward in all directions, marking the boundary between possible and impossible paths. Anything slower than light must remain inside that cone of possible futures. Near a black hole, the cones tilt inward. Close to the horizon, the outward possibilities narrow. At the horizon, the outward edge of the cone lies along the boundary itself. Inside, the entire cone points towards smaller radius. This means that even light, aimed in the most outward local direction, still belongs to an inward future. A flashlight still works. The beam leaves the lamp at light speed. Locally, physics appears normal in a small freely falling frame, but the global future of the beam is no longer escape. It is carried inward with everything else. Space has not vanished, time has not stopped. Their roles have shifted in a way that turns escape from difficult into meaningless. This role exchange also changes how survival feels as a concept. A living being survives by continuing its internal order through time. Cells repair damage, chemical gradients are restored, memory persists in changing patterns of matter, and the organism remains itself from one moment to the next. Inside a black hole, that personal time may still unfold for a while, especially after crossing the horizon of a very large black hole. The falling body may not notice the horizon locally. A heart might beat, a machine might compute, and a clock might record readings, but each next moment has fewer possibilities than it would outside. Survival continues only along a path whose end is built into the structure of the region. The organism may live for moments, but it cannot make a home in a future that ends as a boundary of space-time for an extended object. This interior geometry also means that different directions have different meanings. In some simplified descriptions, one direction is stretched while others are compressed. The fall can be imagined as entering a universe that is collapsing in one sense while lengthening in another. This is not an ordinary room shrinking around a traveller. It is the fabric of possible distances and times changing as the singularity becomes the shared future. The word centre becomes inadequate because there is no stable central place that can be circled from within the non-rotating interior. The singularity is everywhere in the future of the infalling object, not off to one side. A map drawn outside the black hole may point toward the middle. A map carried inside becomes a map whose end is temporal. The geometry also explains why engines cannot solve the problem. Outside the horizon, thrust can change destiny. A rocket fired outward can raise an orbit, delay a fall, or escape if enough energy is available. Inside the horizon, firing outward does not create an outward future in the global sense. It can alter the path before the end, but it cannot turn the final boundary into an avoidable object. The black hole is not defeated by acceleration because the issue is not lack of speed. The issue is the direction of all future directed paths. Even a beam of light lacks an escape route, not because it fails to move fast enough, but because inside the horizon, moving into the future is already moving deeper. This does not mean the interior is featureless. A falling observer may witness strange patterns of light and darkness. Light from the outside universe can still arrive from behind for a time, warped and shifted by curvature and motion. Radiation and matter that fell in earlier may occupy different parts of the interior history. In rotating black holes, the structure becomes more complex, with frame dragging, inner horizons, and possible instabilities. But the central lesson from the simplest geometry remains. Crossing the horizon changes the relationship between motion and future. It turns the singularity from a distant object into an unavoidable event. It makes survival depend not only on force and radiation, but on whether space-time itself continues to offer a lasting sequence of moments in which structure can remain organized. Classical general relativity says that this sequence ends. The theory predicts that curvature grows without limit, and the known description fails at the singularity. That failure is not a small technical inconvenience. It is a warning that the theory has reached its edge. When curvature becomes extreme enough, quantum effects are expected to matter, but no complete and tested theory yet describes the final interior. It may be that the singularity is replaced by something else, a quantum region, a bounce, a transition, or a boundary of a kind not yet understood. It may be that the classical picture captures the direction of the fall, but not the true final state. Any answer beyond that must be cautious. Known physics can describe the closing of escape and the inward tilt of futures. It cannot yet give a fully trusted account of what happens when the mathematical end is reached. Inside the geometry, survival is therefore both clearer and more mysterious. It is clearer because the event horizon does not merely surround danger, it changes the structure of possible futures. It is more mysterious because the final future predicted by relativity is also where relativity stops being complete. Something may cross the horizon intact. Something may continue to function for a finite time. Something may even carry memory, chemistry, or measurement deeper into the black hole than intuition expects. But in the classical interior, there is no lasting inside to settle into, no central landscape to explore, and no route that turns away from the end. The black hole's deepest power is not a crushing surface, but a future that has become one way. Beyond the horizon, the center is tomorrow, and tomorrow cannot be avoided. Matter inside a black hole does not enter a deeper version of ordinary darkness. It enters a place where ordinary forms of matter are stripped of the conditions that let them behave as matter in the familiar sense. Outside the horizon, atoms can make minerals, oceans, membranes, metal, bone, dust, and gas, because the forces inside them remain stronger than the local differences in gravity across their tiny structures. Electromagnetism holds electrons near nuclei. Nuclear forces bind protons and neutrons. Chemistry builds long chains, folds proteins, stores energy, and lets living systems maintain order. These arrangements are not weak by everyday standards. A crystal can endure pressure. A spacecraft can survive vacuum, radiation, and acceleration. But inside a black hole, the question is not only whether matter is strong, it is whether the surrounding geometry gives matter enough sameness from point to point to keep structure meaningful. As the fall continues inward, curvature rises, and the difference between neighbouring paths can become stronger than the bonds that make objects whole. At first, the pressure is not felt as pressure. A freely falling object does not feel gravity in the same way a person feels weight on a planet. It floats. Its pieces float with it. The early interior of a large black hole may be quiet enough that ordinary matter continues for a time. A metal surface remains metal. Water remains water if temperature and radiation permit it. A living cell remains a living cell if its chemistry has not been damaged before the crossing. Yet the calm is conditional. The deeper fall strengthens tidal strain, and the strain does not respect the categories that matter uses to organize itself. First it challenges large shapes, pulling distant ends apart. Then it challenges smaller shapes, forcing neighboring regions of the same object to follow paths that diverge. When the gradient becomes severe enough across the scale of a body, the body fails. When it becomes severe enough across organs, tissues fail. Across cells, membranes and internal structures lose coherence. Across molecules, bonds are stretched, distorted, and broken. Across atoms, even the idea of a stable local environment begins to fade. This progression is not a sequence of impacts. It is the tightening of space-time around every attempt at order. Living systems are especially fragile because life is more than material endurance. A rock can be broken and still remain rock fragments. A metal plate can bend and still be metal. Life depends on a constant choreography of unequal states held in balance. Cells keep some ions inside and others outside. Proteins hold precise shapes. Genetic molecules must remain readable. Water must remain liquid. Energy must move through controlled pathways. A living organism is a storm kept small and organized, inside a black hole. Even if the first horizon is crossed safely, that organization faces increasingly hostile conditions. Tidal forces can disrupt circulation and nervous signaling in larger bodies. Radiation can alter chemical bonds and destroy stored information. Heating from surrounding and falling matter can overwhelm cooling. Accelerations relative to nearby streams of material can turn dust grains or plasma into dangerous projectiles. No single danger needs to be dramatic. A living system ends when enough of its internal order can no longer be maintained. For a simple microbe, the margin is wider. A bacterium is small, and smallness reduces tidal stress across its body. A dormant spore or frozen cell might remain physically intact longer than a complex animal, but it still requires chemistry to retain meaning. If molecular bonds are damaged, if radiation shreds genetic material, if the membrane loses its boundary, survival becomes only preservation of debris. This same distinction applies to more extreme ideas of life. A hypothetical machine intelligence carried on hardened hardware, or a self-contained probe designed for crushing environments, might outlast ordinary biology. It might cross a supermassive horizon while still computing. It might record gravitational gradients and radiation levels. But computation depends on stable states, on memory that can remain one thing rather than another, on signals that arrive, on circuits or quantum systems that preserve contrast. The black hole interior eventually attacks these requirements. Strong curvature and growing tidal stress can deform the device. Radiation can flip stored bits, melt materials, or produce cascading failures. If the path passes near unstable inner regions of a rotating black hole, incoming energy can be amplified far beyond what any known shielding can handle. Machine survival may extend the timescale, but it does not change the deeper problem. Information needs a physical carrier, and every carrier is made of matter that must remain organized. Planets fare worse, not because their matter is weaker in every part, but because their size gives tidal forces a larger lever. A planet crossing a gentle supermassive horizon might not break at the boundary, but it cannot remain a planet indefinitely. Its near side and far side no longer share the same future closely enough. Oceans shift first, atmosphere distorts, crust and mantle stretch, and the world begins to lose the roundness given by its own gravity. Deeper in, it becomes a stream, a long ribbon of rock, metal, vapor, and plasma. A star entering a black hole faces a related fate if the encounter is close enough. The star is not swallowed like a marble. It is drawn apart by the difference in gravity across its diameter. Some material may be heated into a disk outside the horizon if the star is torn apart before crossing. Some may fall inward. In either case, the black hole converts coherent worlds into flows, and flows into simpler descriptions of energy, momentum, and curvature. The language of objects gives way to the language of fields. This is why survival inside a black hole cannot mean simply that some matter continues to exist. Matter almost certainly continues along the fall until the classical description breaks. The harder question is whether any pattern survives. A living organism is a pattern, a memory is a pattern, a planet is a pattern, a molecule is a pattern. Even an atom is a pattern of fields and particles in a stable relation. Black holes are not only dangerous because they contain strong gravity, they are dangerous because they make stable relations increasingly hard to preserve. Near the singular future of a non-rotating black hole, classical relativity predicts unbounded curvature. No known material strength, chemical bond, or nuclear arrangement can be expected to remain intact all the way through. The theory itself signals that its own language has reached a limit, but before that limit, it gives little comfort to ordinary structure. Everything extended is driven toward distortion. Everything organized must fight the loss of the conditions that let organization persist. Radiation adds another layer to the question. A quiet black hole may have little surrounding light compared with an active one, but the universe is never completely empty. There is cosmic background radiation, starlight, particles, and the remains of whatever has previously fallen in. For a falling observer, the energy of incoming radiation depends on motion and position. In some parts of the descent, light from the outside can appear shifted and concentrated. In rotating black holes, near the inner horizon, tiny disturbances may be magnified into severe energy densities. This means that survival is not decided by gravity alone. A traveller may be spared from immediate stretching at the outer horizon, only to meet a later region where radiation becomes the main threat. The black hole interior is not a clean vacuum laboratory. It is crossed by histories, by signals, by matter that entered before and after, all shaped by a geometry that can amplify small differences into catastrophic ones. In the end, pressure inside a black hole is not pressure in the simple sense of a weight pressing down on a surface. It is final pressure in a broader meaning. It is the pressure placed on every distinction matter tries to maintain. Near the horizon of a large black hole, those distinctions may survive. Body and space, clock and signal, inside and outside of a cell, memory and noise, object and environment can still retain meaning for a while. Deeper in, each distinction is tested. A living system can survive only where chemistry continues. A machine can function only where states remain stable. A planet remains a planet only where gravity, strength, and distance can keep its pieces in shared form. As curvature rises, the black hole reduces these possibilities. It does not need a blade, flame, or solid surface. It lets geometry do the work. Something material may survive the crossing. Something organized may survive briefly beyond it. But known physics gives no reason to think life. Ordinary matter in complex form, or any familiar structure, can endure the full descent. Biology meets broken physics, and biology is built for places where the future is wide enough for repair. Inside the black hole, the future narrows until repair itself has nowhere left to act. The idea of a gentle singularity sounds almost like a contradiction. Singularities belong to the harshest language in physics, places where equations point toward infinite curvature, infinite density, and the end of ordinary prediction. Gentle belongs to worlds of low force, slow change, and survivable passage. Yet in the study of rotating black holes, the word appears because not every mathematical breakdown looks the same to something falling through it. A singularity is not always imagined as an instant crushing point in every model. Some are space-like, lying across the future like an unavoidable ending. Some are time-like in idealized equations, more like a dangerous line that might be approached or avoided. Some are strong, meaning they tear apart any extended object without mercy. Others can be weak in a precise mathematical sense, meaning the tidal distortion along a path may remain finite even though certain measures of curvature become extreme. This does not make them safe. It only opens the smallest possible space for asking whether passage, rather than immediate destruction, can be discussed at all. The path to this question begins with the inside of a rotating black hole. In the ideal Kerr solution, the interior contains an outer horizon, and then an inner horizon. The outer horizon is the familiar boundary of no return. The inner horizon is stranger. It marks a boundary beyond which the predictive structure of the space-time becomes uncertain in the classical equations. In a perfect, empty mathematical black hole, this region leads toward possibilities that seem almost unreal, including extensions beyond the first interior. But real black holes are not perfect or empty. They absorb light, gas, gravitational radiation, and the faint background of the cosmos. The inner horizon becomes a place where these incoming disturbances can be amplified by extreme blue shift. This amplification can create mass inflation, a runaway growth in effective internal energy. For a traveller, that sounds catastrophic, and in many analyses it is. The inner horizon may become a singular region produced not by a central point, but by the piled-up history of everything that has fallen through the horizon before. Still, the nature of that singular region may be subtle. A strong singularity destroys any object by stretching and squeezing it without limit. A weak singularity may allow certain objects, idealized as small, freely falling observers or mathematical fields, to pass through without infinite tidal crushing along that exact path. The curvature can become unbounded in some descriptions, while the total distortion experienced over the crossing remains finite. This is the narrow meaning of gentle. It does not mean comfortable. It does not mean biologically friendly. It does not mean an astronaut emerges unharmed into a clear new domain. It means that the local tidal impulse may not be enough, by itself, to reduce every possible falling object to zero volume at the crossing. The distinction matters because survival inside a black hole is otherwise quickly swallowed by absolute words. If every singularity is treated as equally final in every sense, the discussion ends too early. If weak singularities exist in realistic interiors, then the question becomes more layered. Something might pass through one kind of internal boundary while being destroyed by another. Something might survive the geometry but not the radiation. Something might preserve mathematical continuity while losing every feature that would make it alive. Older rotating black holes add another speculative thread. Over long cosmic time, a black hole settles after the violence of its birth. The wild ringing of space-time fades. The immediate collapse that created it becomes part of its past. It may continue to absorb faint radiation and occasional matter, but in a quiet environment its exterior becomes close to the stable rotating form described by relativity. In some speculative discussions, an old and massive rotating black hole could contain inner structures that are less violently tidal along certain paths than the direct central destruction expected in simpler models. A falling object entering at high speed might, in principle, encounter a weak internal singularity before stronger destructive regions catch it. This remains uncertain because the interior is hidden and because small perturbations can dominate there. The idea is not a prediction that life can pass through. It is an admission that the equations have corners where the word impossible must be used carefully. For biology, the opening is probably too small to matter. A weak singularity in the mathematical sense is not a habitat. It does not provide air, temperature stability, shielding, nutrients, or a long sequence of calm moments. It may not even provide a reliably smooth passage for anything extended beyond ideal approximations. A living organism is not a point following a line. It has size, fluids, electrochemical signals, delicate membranes, and memory stored in physical arrangements. Finite tidal distortion can still be lethal if it is large enough, rapid enough, or combined with radiation. The inner horizon environment may involve streams of incoming energy from the outside universe and from matter that fell earlier. Even if the formal tidal forces along a special path are limited, the surrounding conditions may destroy chemistry. The word gentle becomes almost deceptive unless it is held inside its technical frame. Gentle compared with an infinitely destructive singularity does not mean gentle compared with any place where life has ever existed. For a machine or a small probe, the question is only slightly more open. A hardened device could be built smaller, stronger, and less dependent on liquid chemistry than a living body. It could cross a large outer horizon intact. It could store data redundantly and continue operating through stronger gradients than biology can tolerate. If an inner weak singularity lay along its path, and if radiation and instability were not overwhelming, perhaps some mathematical version of the probe's world line could continue past the singular boundary. But the probe could not report this to the outside universe. Its data would remain sealed. If it were damaged beyond function, no one outside could know the exact point of failure. If it somehow continued, no signal could return to confirm the most important discovery. This makes gentle singularities scientifically haunting. They may be physically meaningful and yet observationally inaccessible, present as possibilities in equations but hidden from the universe that could test them directly. Quantum gravity may change the whole story. Singularities in classical relativity often signal not a real infinite object, but the breakdown of the theory being used. When curvature grows extreme, quantum effect should become important, and the singular boundary may be replaced by something finite but unfamiliar. A weak singularity might become a transition region. A strong one might be softened by quantum structure, or it might remain effectively final for any organized matter. There may be no singularity at all in the completed theory, only a domain where space-time is no longer smooth enough to be described by the old geometry. But these possibilities are not established facts. They are careful ways of naming the unknown. The survival question cannot be answered by hope placed inside a missing theory. It can only be framed known classical equations allow different kinds of singular behavior, and some of the weaker kinds do not automatically imply immediate infinite crushing along every path. Beyond that, certainty fades. The deepest difficulty is that survival has layers. A mathematical path may survive if it can be extended through a boundary. A small object may survive if tidal distortion remains finite. A physical pattern may survive if its information remains encoded in matter or fields. A living thing survives only if its organized processes continue. A person survives only if the body and the conscious activity of the brain remain integrated. Gentle singularities, if they exist, might help with the first layer and perhaps with the second under special assumptions. They do little for the last layers. The interior of a black hole is not merely a dangerous landscape. It is a place where the definitions of landscape, time, and continuation are under stress. A curve through space-time may continue while everything that gave it ordinary meaning is gone. This is the smallest opening offered by rotating interiors. It is not a doorway drawn in the dark, not a promise of passage, not evidence of hidden civilizations living beyond the horizon. It is a narrow scientific caution against making the black hole simpler than it is. Some singularities may be crushing walls. Some may be unstable inner boundaries. Some may be weak enough in one measure to let idealized motion continue. But none of them, within known physics, turns the inside of a black hole into a place where life can endure. The gentleness is relative, technical, and uncertain. It leaves the question open only at the edge of theory, where the strongest known gravity meets the incompleteness of the laws used to describe it. The deepest answer to survival inside a black hole is hidden behind a missing law. General relativity describes gravity as the curvature of space-time, and it works with extraordinary precision across planets, stars, galaxies, and the waves released when black holes collide. Quantum mechanics describes the small world of particles, fields, uncertainty, and probability, and it works with equal precision inside atoms, light, matter, and the structure of every known material. Each theory is one of the great foundations of modern science. Each has passed tests far beyond everyday experience. Yet inside a black hole, especially near the region that classical relativity calls a singularity, the two foundations must meet. Matter is compressed toward extremes. Curvature grows without ordinary limit. Energy, information, and space-time itself become part of the same question. In that place, relativity says its own equations are being pushed to a point where they no longer give a complete physical answer. Quantum mechanics says the world should not be described by smooth certainty alone. The survival question reaches a wall because the law that should unite them has not yet been confirmed. A singularity in classical relativity is not merely a very dense object. It is a sign that the mathematical description has become incomplete. The equations predict that curvature grows without bound, and that paths through space-time end. But infinities in physics often warn that the model has been carried beyond its domain. When a theory produces an infinite density or an infinite curvature, nature may not actually contain an infinite thing. Instead, the theory may be missing a piece. This has happened before in science. Older descriptions failed at extreme speeds, extreme smallness, or extreme gravity, and deeper theories replaced them without making the older ones useless. Newtonian gravity remains excellent for ordinary calculations, even though relativity gives the deeper account. Classical electromagnetism remains powerful, even though quantum theory reveals a smaller layer. In the same way, general relativity may remain the right guide for horizons, orbits, and large-scale curvature, while failing at the final interior. The unknown is not whether relativity is valuable. It is what replaces its singular endpoint. Quantum gravity is the name given to the missing framework that would describe gravity when quantum effects can no longer be ignored. It is not one finished theory. It is a field of attempts and clues. Some approaches suggest that space-time may not be smooth at the smaller scales. It may have a discrete structure, or emerge from deeper quantum relationships. Some suggest that information, entanglement, and geometry are linked in ways that ordinary intuition cannot picture. Some propose that singularities may be softened, avoided, or replaced by transitions. Others leave open the possibility that black holes end in states so strange that familiar words such as inside, time, and object become approximations. None of these ideas, by itself, gives permission to claim that life can survive the descent. They show only that the classical picture of inevitable crushing may not be the final microscopic story. The absence of a complete theory creates caution in both directions. It is too strong to say with absolute certainty that the singularity is a literal infinite point where every physical quantity truly becomes endless. It is also too strong to say that quantum gravity will provide a passage, a bounce, or a safe continuation for organized matter. The unknown does not automatically become hopeful. A quantum replacement for the singularity could still be fatal to every possible organism and every stored memory. It might be finite but violent, structured but uninhabitable, lawful but destructive. Survival requires more than the removal of infinity. It requires conditions under which matter can remain organized and processes can continue. Quantum gravity may change the final fate, but it does not erase the earlier hazards of tides, radiation, inner horizon instability, and the loss of all escape paths. A softened singularity could still be the end of anything resembling life. One sharp clue comes from black hole thermodynamics. Black holes behave as if they have temperature and entropy, where entropy measures hidden microscopic arrangements. The temperature is extraordinarily low for large black holes, but it is not zero. Quantum theory in curved space-time predicts that black holes slowly emit Hawking radiation, losing mass over immense times. This idea connects gravity, quantum fields, and information in a way that no ordinary star or planet does. It suggests that black holes are not simply perfect prisons. They have a quantum life, however faint and slow. But Hawking radiation is mostly about the horizon and the long future of the black hole as seen from outside. It does not yet reveal what happens to an observer who has already fallen deep inside. It shows that quantum effects matter near black holes. It does not turn the interior into a known place. The problem of information makes the mystery sharper. If matter falls into a black hole, what happens to the information that describes its quantum state? In ordinary quantum theory, information is not simply erased. The evolution of a closed system preserves it in a deep mathematical sense. But the classical black hole seems to hide information behind a horizon. And then, if Hawking radiation is purely thermal, perhaps let the black hole evaporate without returning the details. This tension is called the black hole information problem. Many physicists now suspect that information is not destroyed, but how it is preserved or returned remains one of the central puzzles for survival. The information problem shifts the meaning of endurance. Even if a body is destroyed as a body, perhaps some information about it is not lost from the universe, but that is not biological survival. It is not a person continuing to experience time. It is not a cell remaining alive. It is a more abstract survival, and even that is still being understood. Some speculative ideas imagine that the black hole interior could avoid a final singularity through a bounce, where collapse gives way to expansion in another region. Others imagine that space-time near the core becomes quantum foam, a dense web of fluctuating geometry, or that the interior connects in some limited way to a broader structure. These ideas are interesting because they show how collapse might not be the last word in a completed theory, but they are not observations. They are not established maps. They do not say that an organism could pass through and remain itself. A bounce severe enough to replace a singularity could still crush, heat, scramble, or transform ordinary matter beyond recognition. If a new region formed beyond the black hole, it might inherit energy or information in a form unrelated to a surviving traveller. The difference between a cosmos continuing and a creature surviving is enormous. Quantum gravity may allow the first without allowing the second. The missing law also affects the meaning of time. In quantum theory, time often plays the role of an external parameter, a background against which systems change. In general relativity, time is part of space-time itself, flexible and shaped by gravity, inside a black hole, where the geometry is extreme. These roles no longer sit easily together. If space-time is quantum, then time itself may not be fundamental in the way ordinary experience suggests. The final moments of a fall may not be described by a smooth clock approaching a sharp endpoint. They may involve a domain where the usual sequence of before and after becomes emergent, approximate or limited. This is profound, but not a loophole for life. Life depends on ordered time. Metabolism, memory, computation, and repair all require a stable sequence of changes. If time becomes deeply quantum or loses its familiar structure, then the conditions for life become harder, not easier, to maintain. Known physics reaches its wall honestly. It can say that a large, quiet black hole may allow something to cross the event horizon intact. It can say that tidal forces eventually rise in the simple interior. It can say that rotating interiors may contain inner horizons and instabilities. It can say that the classical singularity is where the theory stops being complete. Beyond that, the answer becomes conditional on a theory not yet confirmed by experiment. The most careful conclusion is neither pure destruction stated with false finality nor fantasy dressed as science. It is a layered answer. Ordinary life cannot be expected to survive deep inside a black hole under known physics. Matter may persist for a time. Information may have a fate more subtle than disappearance. The final singularity may be replaced by quantum structure. But no known law provides a stable path, a safe chamber, or a continuing environment for living systems. The question survives because physics itself is unfinished at the deepest point. Certainty reaches its wall, and beyond that wall there is not permission to invent an answer, only the quiet recognition that the universe has hidden one of its most important rules behind the horizon. A black hole appears from the outside as an ending. Matter falls in, light fails to return, and the wider universe receives only the fading evidence of mass, spin, charge, and gravitational influence. The boundary that is not a surface seals every message away. Yet the same object that looks like an ending from outside has sometimes been imagined, cautiously and speculatively, as the beginning of something else from within. This idea grows from the uncomfortable similarity between two extreme stories in physics. In one story, matter collapses inward until classical relativity predicts a singularity. In another, the observable universe seems to have emerged from an early state that was hot, dense, rapidly expanding, and beyond ordinary intuition. Collapse and birth are not the same event in standard cosmology, and no observation shows that every black hole creates a universe. But the resemblance is provocative enough that some scientists have asked whether the interior of a black hole could avoid final destruction by becoming a new expanding region, hidden behind the horizon of the parent cosmos. The first step is to keep the known facts separate from the speculation. Known black holes form when massive stars collapse, when compact remnants merge, or when enormous amounts of matter gather in galactic centers. Their horizons can be described by general relativity, and their effects can be observed through stellar orbits, accretion disks, gravitational waves, and the shadows cast by hot gas bending around them. Known cosmology describes an expanding universe whose early history is supported by the cosmic microwave background, the abundance of light elements, and the large-scale distribution of galaxies. These descriptions are successful, but neither says directly that a black hole is a universe seed. The connection appears only near the limits of the theories, where relativity predicts singularities and where quantum gravity is needed. At that limit, collapse may not simply end in an infinite point. It may reveal that the old equations have run out of language. If a singularity is replaced by some quantum region, then the interior future of a black hole might not be pure termination, it could be transformation. One speculative possibility is a bounce. In ordinary language, a bounce suggests matter falling inward, reaching some smallest state, and then expanding again. In deep gravity, the idea is far less simple. There may be no ordinary space into which the collapse rebounds. The expansion might occur in a new space-time region, causally cut off from the universe that made the black hole. From the outside, the black hole remains a dark object with a horizon. It may persist for an immense time and slowly lose mass through quantum radiation. From the inside, if the bounce picture were correct, the final inward collapse might become the beginning of expansion for a daughter universe. The parent universe would not see galaxies forming inside. No telescope could look through the horizon and watch creation unfold. The new region, if it existed, would be locked behind the same boundary that prevents any signal from returning. This makes the idea both elegant and frustrating. It offers a way for collapse to become birth, but hides the birth from confirmation. Another route comes from the strange interior geometry of black holes. In the simplest non-rotating case, the singularity lies in the future of anything that crosses the horizon. In rotating cases, the mathematical interior grows more complicated, with inner horizons, ring singularities, and extensions that hint at other regions. Most of those extensions are likely unstable in realistic black holes, because tiny disturbances can become violently amplified. Even so, they show that relativity does not make the word inside as simple as a room behind a door. The interior can have global structure that is difficult to compare with ordinary space. If quantum gravity alters the would-be singular region, the continuation may not resemble passage through a tunnel. It may be a change of space-time phase, where the collapsing geometry gives rise to a new expanding geometry. In that picture, the black hole is not a doorway for a traveller, but a boundary between cosmic histories. A universe born this way would not necessarily look like its parent. The conditions at a quantum bounce, if such a bounce occurs, might scramble or reset many details. Some speculative models suggest that physical constants could vary slightly between generations, Others keep the laws largely the same but allow different initial conditions. If black holes produce daughter universes, then universes that make many black holes would also make many descendants. This leads to the idea sometimes called cosmological natural selection, where cosmic lineages that favour star formation and black hole formation become more common across an unseen multiverse of descendants. The idea is bold and not established. It cannot yet be treated as a confirmed explanation for the laws of nature. Still, it is intriguing because the same ingredients that produce many black holes also produce heavy elements, long-lived stars, planets, and the chemical richness that life uses. In such a view, a universe good at making black holes may also, indirectly, be good at making places where life can appear. This does not mean life survives the fall into a black hole. It changes the scale of the question. The organism that crosses the horizon does not continue as an organism into the hypothetical daughter universe. The crushing, heating, radiation, and loss of ordered structure remain severe in known physics. A black hole as a cosmic seed would not be a refuge for bodies. It would be more like a reproductive event for space-time itself. Matter and information from the parent universe might contribute to the conditions of the new region in ways not yet understood, but a living creature would not ride through intact and step into a new sky. Even if a daughter universe forms, the survival involved is not personal survival. It is not biological survival. It is a far more abstract continuity collapse feeding expansion, one cosmic domain giving rise to another. The death of organized matter becoming part of a larger birth that has no memory in any familiar sense. The information problem makes this more delicate. If information is preserved in black hole evolution, then the complete story of what falls in may not be erased. Some theories place information on or near the horizon in subtle quantum degrees of freedom. Others connect interior and exterior descriptions in ways that challenge ordinary ideas of locality. If a black hole also leads to a daughter universe, then the fate of information becomes harder to state. Does information remain with the evaporating parent black hole, pass into the new region, or exist in a deeper description that makes both answers partial? No tested theory decides this. For survival, information preservation is not the same as a surviving self. A living mind reduced to inaccessible quantum correlations is not a continuing life. Cosmic seed ideas widen the meaning of continuation, but they also strip it of ordinary comfort. There is also a problem of evidence. The horizon prevents direct observation of any interior universe. A daughter cosmos, if causally disconnected, cannot send a signal back to the parent. Its stars, if it has stars, shine into its own space-time, not ours. Its galaxies, if they form, belong to a history sealed from the outside that made it. This means the idea must be judged indirectly through mathematical consistency. Possible predictions about physical constants, black hole populations, or traces in cosmology. So far, no decisive evidence shows that black holes reproduce universes. The idea remains speculative, an attempt to think carefully where known theories point toward incompleteness. Its value may be less in providing an answer than in showing how large the question becomes when gravity is pushed to its limit. A black hole may be an end for matter and a beginning for geometry, or it may simply be an end in a way no current theory can fully describe. Both possibilities are humbling. If black holes are cosmic seeds, then the universe is not a closed story of formation followed by decay. It is part of a deeper pattern in which collapse may open into hidden expansion, where the darkest objects become silent origins that no parent cosmos can witness. But the known answer remains restrained. Nothing familiar survives the full descent as itself: life, machines, planets. and stars meet forces and uncertainties that erase their ordinary forms. The possible survivor is not the traveller, but perhaps the conditions, information, or deeper structure carried into a new phase of space-time. Collapse hints at birth, but the hint is not proof. It rests at the boundary where relativity, quantum theory, and cosmology meet without yet becoming one law. From outside, the black hole stays dark. From within, perhaps there is only destruction, or perhaps, beyond the reach of every returning signal, the inward future turns into a new outward beginning. Life beyond the horizon is not easy to imagine, because the horizon takes away the usual meanings of life, place, and future. A living thing is not only atoms arranged in a certain shape, it is a process that keeps renewing itself against disorder. It needs usable energy, moving signals, repair, and a surrounding world stable enough for those actions to matter. Outside a black hole, even in harsh places, survival can be described through environment. A microbe may survive in ice, acid, salt, radiation, or deep rock because its chemistry still has a setting. A probe may survive near a planet or star because its materials still have predictable stresses and its circuits still have time to work. Inside a black hole, the problem changes. There may be a brief region after the horizon of a giant black hole where local physics remains ordinary enough for a body or machine to continue, but the horizon has already removed the larger environment from reach. No signal can return. No rescue can arrive. No orbit can become a home in the simple interior. Survival stops being a question about living in a place and becomes a question about what kind of continuation can still have meaning when the outside future is closed. The first and strictest meaning of survival is biological survival. In that sense, known physics is severe. A living organism might cross the event horizon of a sufficiently large black hole without immediate harm if the surrounding space is quiet and tidal forces are weak. It might carry warmth, oxygen, internal chemistry, and consciousness for some finite time. But this is not survival in the durable sense. It is a continuation after a boundary, not an adaptation to an interior world. The organism remains dependent on conditions that cannot last indefinitely. Tidal forces rise, radiation may grow, internal processes face increasing distortion. The singular future of the simple black hole leaves no stable region where metabolism can continue. Even a dormant microbe, stripped down to minimal activity, still depends on molecular order. Its genetic information must remain readable. Its chemistry must not be scrambled into useless fragments. Black holes do not provide a gentle ecological niche. They provide a path inward where the meaning of ecology disappears. A second meaning is mechanical survival. A probe could be smaller, stronger, colder, and more resistant than any organism. It could be built to record until the last possible moment, using redundant memory, shielded electronics, and instruments designed for extreme acceleration and radiation. Such a machine could survive deeper than biology. It could cross a horizon that no living body should approach. It could store measurements of tidal gradients, light shifts, and particle impacts. Yet the same boundary makes its discoveries private. The probe cannot send results back after crossing. The machine may continue to function, but its scientific purpose is sealed away. Later, as curvature and radiation intensify, even its hardware loses the stable differences required for computation. A bit of memory must be one state rather than another. A signal must cross a circuit before noise erases it. A structure must remain aligned well enough to hold a pattern. Inside the deep black hole, each of these demands becomes harder. Mechanical survival can last longer than biological survival, but it still depends on organized matter and organized matter has no known path through the final classical interior. A third meaning is structural survival. Perhaps the body dies, the machine fails, and the planet is torn apart. But some pattern continues in another form. The atoms that once belonged to a living cell may still fall inward. The energy, momentum, and charge associated with an object may still contribute to the black hole. In a broad physical sense, nothing simply vanishes at the horizon from the point of view of the whole theory. Though the details remain deeply debated, the black hole gains mass and angular momentum. Its gravitational influence outside reflects the total contribution of what entered. This is a kind of survival only by abstraction. A person is not preserved because the black hole becomes slightly more massive. A forest is not preserved because its particles add to a gravitational field. The pattern that made the matter alive has been lost to any familiar description. Still, physics treats patterns as information, and black holes force the question of whether information is ever truly destroyed. Information survival is the most subtle version. In quantum theory, the complete state of a closed system is expected to evolve in a way that does not erase information. Black holes challenge that expectation because they hide matter behind horizons and slowly radiate over immense time. If the radiation eventually carries information back out in an encoded form, then the details of what fell in may not be lost from the universe. If so, something survives beyond the destruction of every ordinary structure, not the organism, not the memory as experienced, not the machine as a functioning probe, but the underlying information in a transformed and inaccessible form. This would be survival without continuity of self. Information preservation may protect the universe from forgetting in a fundamental sense. It does not protect life from dying as life. There is also a speculative cosmic meaning of survival. If the interior of a black hole gives rise to a new expanding region, then the fall of matter may contribute to conditions beyond the parent horizon. The black hole might act as a seed, not for a creature moving safely through it, but for a new domain of space-time whose history begins where the parent universe sees only darkness. In that case, survival becomes almost unrecognizable. It is not the survival of the falling astronaut microbe or probe. It is the continuation of physical law, energy, or information into a daughter cosmos, if such a cosmos exists at all. The original structures would not remain intact. Their identities would not carry over as ordinary objects. But the collapse might still feed a larger continuity, as a star's death feeds heavy elements into later worlds without the star surviving as a star. The analogy is limited, because a daughter universe would be hidden behind a causal boundary and shaped by unknown quantum gravity. Yet it shows how the word survival can stretch from biology into cosmology. Something may fail completely at one scale while contributing to emergence at another. This widening of meaning can be tempting, but it must stay disciplined. It would be easy to turn the black hole into a mythic passage, a dark gate where lost things are reborn. Known science does not support that image. The horizon is not an entrance to a habitable realm. The interior is not a secret shelter. A new universe, if one forms, is not an afterlife for the objects that made it possible. The known answer remains grounded in damage, finite proper time, causal isolation, and the breakdown of classical prediction. What changes is the philosophical shape of the question. To survive as a body is one thing. To survive as a pattern is another. To survive as conserved information is another still. To survive as part of the conditions for new space-time is so far from ordinary survival that it may need a different word. Black holes force these meanings apart. They show that continuation can exist without rescue, preservation can exist without experience, and physical influence can persist after identity is gone. Life itself, as science understands it, belongs to regions where time has room. Energy flows gently enough to be harnessed, and structure can repair itself faster than disorder destroys it. Planets provide such regions for a while. Stars provide energy for them. Chemistry explores them through oceans, rocks, atmospheres, and cells. A black hole interior is the opposite kind of setting. It narrows the future instead of opening it. It hides information instead of sharing it. It carries matter toward conditions where known descriptions lose their stability. If anything survives beyond the horizon, it is likely not life in the warm, organized, self-maintaining sense. It may be matter for a short time, a machine for a shorter scientific purpose, information in a deeply encoded form, or perhaps the seed of a wider geometry. The living creature does not become at home there. The universe may carry some trace forward, but it does not keep the creature whole. This is the quiet turn in the question. Could anything survive inside a black hole? The answer depends on what counts as anything and what counts as survive. A body may survive the first crossing, a structure may survive for a while. Information may survive in a form that no mind can read. A new universe may, in speculation, carry forward conditions born from collapse. But life as an ongoing process has no known refuge beyond the horizon. Survival changes meaning there because the black hole strips away the ordinary world that gives the word its weight. The last quiet answer begins where certainty and humility meet. A black hole is not a monster with a mouth, and it is not a secret world waiting behind a dark shell. It is a place where space-time itself has changed the future available to anything that enters. At the horizon of a very large and quiet black hole, survival is possible in the limited and surprising sense that a body may cross without immediate destruction. The boundary is not a surface. It does not have to burn or strike. A clock can keep ticking. Chemistry can continue, and a falling laboratory can remain locally normal for a short span of its own time. This fact is real enough to unsettle the simple image of black holes as instant crushers. Yet it is also easy to misunderstand. The horizon is gentle only in some conditions and only at first. Its meaning is not comfort. Its meaning is final separation from the outside universe. Once it is crossed, every future-directed path belongs to the interior. And the question is no longer whether something can turn back. It cannot. The question becomes how long structure can persist while the geometry ahead narrows. Known physics gives the strongest answer in layers. Small black holes are hostile before the interior can even become a meaningful destination. Their tidal forces rise so sharply near the horizon that a large object is stretched and compressed beyond recognition. Larger black holes soften the first crossing because their horizons are wider and their curvature is more gradual at that scale. In them, a spacecraft, a probe, or even a living organism might pass inward intact if the surrounding region is quiet enough. But no known black hole offers a stable interior home. Deeper in, tides grow stronger. Radiation and in falling matter may become dangerous. In rotating black holes, inner horizons may amplify tiny disturbances into violent concentrations of energy. In simple, non-rotating black holes, the singularity lies in the future, not like a stone at the center, but like an unavoidable ending written into the structure of time. To survive for a while is not to survive the black hole. It is to survive the opening movement of a descent whose later chapters become less forgiving. For life, the answer is stricter. Life is not merely the presence of matter. It is matter held in a precise and active arrangement. It is membranes, gradients, proteins, water, memory, repair, and energy flow. It is the ability to keep disorder from winning for another moment. A black hole interior gives no known way for that contest to continue indefinitely. A human body might remain alive past the horizon of a giant black hole for a short private interval, but the future ahead is not a landscape where breath, thought, and repair can carry on. A microbe might endure longer because it is small. A dormant form might preserve its structure through gentler gradients. A machine might outlast biology by being compact, shielded, and redundant. But all of them depend on organized matter. All of them require stable local conditions. All of them need signals and bonds to remain meaningful. As the descent deepens, the interior challenges those requirements more severely than any ordinary environment. There is no known biology suited for a place where the future itself points into rising curvature. For information, the answer becomes stranger. Black holes may not destroy information in the deepest quantum sense, though the full mechanism remains one of the great puzzles of physics. Something about the complete state of what falls in may be preserved, scrambled, encoded, or eventually returned through processes not yet fully understood. This possibility matters greatly for the laws of the universe. It may mean that a black hole does not erase reality from the cosmic record, but information survival is not the same as living survival. A person whose pattern is dispersed into inaccessible quantum correlations has not continued as a conscious observer. A cell whose details remain somehow encoded in the black hole has not remained alive. A spacecraft whose data are sealed beyond the horizon has not completed an experiment for the outside world. The universe may remember in a way no observer can read, but memory in physics is colder and more abstract than memory in a mind. It preserves law, not comfort. For speculation, the answer widens but does not soften. If quantum gravity replaces the classical singularity with something finite, then the deepest interior may not be the literal infinite end predicted by older equations. It may be a quantum region, a transition, a bounce, or a domain where space-time is no longer smooth. If some black holes seed new expanding regions, then collapse may be linked to birth on a cosmic scale. But these possibilities remain unconfirmed. They do not turn black holes into shelters. They do not promise that a falling creature passes through intact. A new universe, if one forms, may carry energy, law, or information forward without preserving the bodies that entered. It may be continuation without identity, emergence without rescue. The speculation is beautiful because it suggests that endings in one frame might become beginnings in another. It is also severe because the thing that begins may not remember the thing that ended. The black hole may be a seed for space-time and still be a grave for every traveller. The careful answer is therefore neither simple yes nor simple no. Could anything survive inside a black hole? Yes, if survival means crossing the event horizon of a sufficiently large, quiet black hole and remaining intact for a finite time. Yes, perhaps, if survival means that some information about matter is not ultimately erased. Yes, in a speculative and cosmic sense, if collapse can feed a new region of space-time, but no. If survival means living indefinitely beyond the horizon, no. If it means escaping after crossing, no. If it means finding a stable inner world where ordinary matter, biology, memory, and purpose continue under familiar laws, the black hole allows temporary endurance, abstract preservation, and speculative continuation. But known physics does not offer ordinary survival. It offers a narrowing road, a private interval, and then a boundary where the known laws themselves stop giving a complete account. This is why black holes remain among the deepest mysteries in science. They are not mysterious because nothing is known about them. Much is known. Their masses can be measured. Their mergers can be heard as gravitational waves. Their shadows can be imaged through the light of hot gas around them. Their effects on stars can be traced across years of observation. General relativity describes their horizons with extraordinary power. Quantum theory hints that they radiate and carry entropy. Yet the most important answer is hidden exactly where no signal can return. The interior is not only dark, it is causally private. Whatever happens, there does not become a message to the outside. The universe permits the question, builds the object, reveals its outline, and then closes the evidence behind an irreversible horizon. The quietness of the final answer matters. Black holes do not need to be exaggerated. They are already extreme. They do not need fantasy to become profound. Their known behavior is enough to bend the meanings of time, space, survival, and information. The safest statement is also the most haunting one. Something may survive the beginning of the inside, but nothing known can survive the whole known journey as itself. The horizon can be crossed. The first moments may be calm. The deeper path may contain uncertainties that still wait for quantum gravity. But the outside universe is gone from the traveller's future. And the traveller's future is being shaped by a geometry that does not open outward again. At the far edge of knowledge, the black hole leaves a final silence. It may be destruction. It may be transformation. It may hide a law that turns the singularity into something no current theory can yet name. Until that law is found, survival inside a black hole remains a layered answer suspended between what is known and what is not. Matter can fall. Time can continue briefly. Information may have a fate still unresolved. But life, as an ongoing and self-maintaining process, belongs to gentler regions of the cosmos. It belongs to worlds where horizons are not one way, where light can return, where repair has time, and where the future is still wide enough to choose. Beyond the last threshold, the question settles into a quieter shape. A black hole remains both known and hidden, measured by the stars that move around it, by the light that bends near it, by the waves it sends through space-time when it merges with another, and by the silence it keeps behind its horizon. The answer does not become simple, but it becomes calmer. Ordinary life belongs to places where change is gentle enough to be repaired, where chemistry can keep its rhythm, where light can leave and return, where a future can remain open. Inside a black hole, that openness is lost. A body may cross the first boundary for a while, especially into the vast dark of a quiet giant. But the crossing is not a homecoming. It is the beginning of a private descent, held away from the rest of the universe by geometry itself. Yet the mystery does not close. At the deepest point, the known laws reach their edge, and beyond that edge may lie a rule still unnamed. Perhaps the final collapse is only collapse. Perhaps quantum gravity softens what appears infinite. Perhaps information is never truly erased, only transformed into a language too deep for present physics to read. Perhaps black holes are endings in one history and seeds in another. None of these possibilities makes the interior safe, and none turns darkness into certainty. They only leave the universe larger than the current answer, so the final thought remains suspended, not in fear, but in wonder. The cosmos contains places where survival changes meaning, where time narrows, where space gives up its exits, and where the most complete theories still fall silent. In that silence, the black hole keeps its question, not as a promise, not as a refuge, but as one of the deepest signs that reality is still unfinished.